start this again. So again, to conduct a hypothesis test, you really need to know what you're trying to prove. And whatever you're trying to prove either becomes the null hypothesis, which you can't really prove, or the alternative hypothesis. And frequently what we're trying to show is that the data that I take in my sample are statistically significant enough to support my alternative hypothesis. That is very frequently what we're trying to do. So the example we ended up with last Wednesday was a baker claiming that the height of his bread was greater than 15 centimeters. And his customer saying, no, I don't believe you. So what the baker is trying to show is the height of his loaves, the average height is greater than the 15 centimeters. And by the nature of the way that's written, that he says that the mean height of his loaves of bread are higher, greater than the 15 centimeters, that becomes the alternative hypothesis. Alternative hypothesis always contains either greater than, less than, or not equal to. It never contains equality. So by the nature of the statement that he says the average is greater than 15 centimeters, that becomes the alternative hypothesis, which we can write as either H subscript A or H subscript 1. It just depends on what your book is writing it. Okay, we're going to use A for alternative. So if that's the alternative, the null hypothesis is mathematically contradictory. It's the exact mathematically opposite of that claim. Now, the mathematical opposite would be less than or equal to 15 centimeters. But your book, your authors point out that you can actually write this as equals. It makes no difference in your testing. Whether you write that as equal or less than or equal to does not matter. When you conduct the test, you're going to look at the alternative. Okay, since the alternative hypothesis we state is that the mean is greater than 15, and when we baked our 10 loaves, we got on average 17, this greater than, the greater than makes this right-tailed. If it's less than, it's left-tailed. If it's not equal to, it's two-tailed. So looking at the alternative hypothesis, if it's greater than, that's a right-tailed test by definition. If it's less than, it's left-tailed. If it's not equal to, it's two-tailed. So what this looks like is we have a normal distribution whose mean is 15, but we got in our sample loaves of bread who were on average 17 centimeters tall. If this is right-tailed, greater than, then what we're looking for is the probability that purely by random chance, we baked 10 loaves of bread and we got 17 inches on average if the actual average is 15. Okay, so what's the probability of me getting something as high as 17, if the average is really 15? 0. Okay, so to find this probability that we get an average in the sample of 17 or greater, we find what is called the p-value. And the p-value is the probability that I get a value, and I probably shouldn't use mu, but we're going to go ahead and use x, greater than 17. What's the probability? Well, I can figure that out. I can use a normal distribution to figure that out, because the normal distribution does find the area under the curve for me. So what is this going to be? This is going to be a normal CDF, lower limit 17, upper limit is infinity with a mean of 15. And then what's the standard deviation? Well, what was the standard deviation? He knows from baking hundreds of loaves, the standard deviation for the height is a half a centimeter. But we're going to use the standard error of the mean in our calculation. We're not going to use the standard deviation of the population. So we're going to take the 1/2 and divide it by our sample size. And he baked what, 10 loaves? So the area under the curve, the p-value, is the normal, the area under the curve is the normal distribution with a lower limit of 17, upper limit of infinity, mean of 15, and a standard deviation of 0.5 squared root of 2. Okay. So go to our distributions, the normal distribution. And this is what we did the other day, except I have it incorrect. So upper is 1. So lower limit 17, upper limit infinity, mean of 15, standard deviation, which is the standard error of the mean. We're going to use that because we're looking at samples, we're looking at averages of samples. So we use the sample error of the mean. Okay, standard error of the mean. And we get, that's 0. That's 0.3606. So you have 36 zeros after the decimal place and before the 5.8 or the 5.8. That's 0. So the p-value is approximately 0. So if the mean height of loaves of bread is really 15, the probability of him baking 10 loaves and getting on average a height of 17 centimeters is negligible. So what about our claim? Well, if the p-value is small, you reject the null hypothesis. And we are going to show you how you compare the p-value to a pre-selected alpha here in a second. But this p is so low that I'm going to reject the null hypothesis that the mean is less than or equal to 15 centimeters. My sample data seems to support the claim that the mean is bigger than 15 centimeters. If the p-value is low, we reject the null hypothesis. And our sample data supports the conclusion brought by our alternative hypothesis. So the sample data supports the conclusion that the mean heights of loaves of bread is greater than 15 centimeters, which is what he said it was. And his customer says, so did he prove his customers wrong? The answer is yes, because he shows from his sample data that the mean height of loaves of bread is bigger than 15 centimeters. That's what a hypothesis test does. And in a hypothesis test, you either reject the null or you fail to reject it. If you fail to reject it, then your sample data doesn't support the conclusion that is brought by the alternative. All right. So our decision and our conclusion. A systematic way to make a decision of whether to reject or not reject the null hypothesis is to compare the p-value to a preset or preconceived alpha. And again, the alpha is the probability of a type 1 error. So if type 1 errors are significant to you, you want to make alpha as small as possible. Typically, alpha is 0.05. That's a very typical number that we use. And if it's not given to you, that's typically what you use, 0.05. When you make a decision to reject or not reject the null hypothesis, do as follows. If alpha, your preset probability of a type 1 error, is greater than the p-value, you reject the null hypothesis. The results of the sample data are significant. There is sufficient evidence to conclude that the null hypothesis is an incorrect belief, and that the alternative hypothesis may be correct. So if alpha is greater than the p-value that you calculate based on your sample data, you reject the null. Your data is significant, and it's sufficient to conclude that the null hypothesis is not correct, and the alternative is. So typically we say the sample data is significant and supports the conclusion, whatever the alternative hypothesis is. If your preconceived preset alpha value is less than the p-value, you cannot reject the null. So your sample data is not significant enough to support the alternative. The results of the sample data are not significant. There is not sufficient evidence to conclude that the alternative hypothesis may be correct. So if you reject the null, your data is significant. If you fail to reject, it is not. When you do not reject H sub 0, the null hypothesis, it does not mean that you should believe that the null hypothesis is true. It simply means that the sample data has failed to provide sufficient evidence to cast serious doubt on the truthfulness of the null hypothesis. So your conclusion after you've made your decision whether to reject or fail to reject the null, you write a thoughtful conclusion. You're going to pick the thoughtful conclusion from choices given to you in the problem. Write a thoughtful conclusion about the hypotheses in terms of the given problem. Man, this guy's over here got the allergy. Something over there is allergic. It's dust or something over there, guys. All right, so if you reject the null, you're going to have in your statement, there is significant evidence. If you fail to reject, then there is not significant evidence. So that's your first clue to decide which one of the four you choose. Okay, and as I described in the bread problem, the alternative hypothesis tells you whether your test is left-tailed, right-tailed, or two-tailed. If the alternative hypothesis contains greater than, mu or p are greater than, that is a right-tailed test. So you're going to be looking for the probability that X is greater than a particular value. If it's less than, if the alternative hypothesis contains the mathematical symbol less than, that is a left tail test. So you're going to be conducting a test and looking for a probability from negative infinity to whatever your test value is. And then if your alternative is not equal to, that is a two-tailed test. And that's the most difficult p-value to find because the p-value is going to be split into two tails. So when you find a probability, you find half of it. You got to double it to get the p-value. So half is in each tail. And you only find one, either that tail or that tail. So you got to double it, find the p-value. Oops. Okay, so here are pictures. If my alternative hypothesis contains a statement that mu is greater than a value, that is a right-tailed test. And the p-value is this probability here. It is the area under the curve from whatever that value is to infinity. So 1 times 10 to the 99. If our alternative hypothesis contains less than, mu is less than a value, then the p-value is right here. And it's the probability from negative infinity to whatever that value is. And then if our alternative contains not equal to, mu is not equal to a value, then we have a two-tailed test, and each tail contains half of my p-value. So when I actually find the area under the curve, I'm going to find the area to the right of this, oops, or the area to the left of that, and I will have to double it to find the p-value. So it either finds over here or over here, depending on how you choose to do your normal distribution. And you're going to get half the area under the curve. You double that to get the p-value. Okay, so let's look at this example. When using the p-value to evaluate a hypothesis test, it is sometimes useful to use the following memory device. I use this all the time. As a matter of fact, when I was standing up there a second ago, comparing the p-value to alpha, I was saying, if the p is low, the null must go. So if the p-value is lower than alpha, then you reject the null hypothesis. If the p is low, the null must go. If it's low, if it's less than alpha, you reject the null. If the p is high, the null must fly. So if the p-value is larger than your preconceived preset alpha, you can't reject the null hypothesis. So you fail to reject it. This memory aid relates a p-value less than the established alpha if the p is low, as rejecting the null hypothesis, and likewise relates a p-value higher than the established alpha. The p is high, and you do not reject the null hypothesis. So we reject the null hypothesis when the p-value is less than alpha. If the p is low, the null must go. The results of the sample data are significant. If we reject the null hypothesis, then our sample data is significant. We don't reject the null hypothesis when the p-value is greater than alpha. If the p is high, the null must fly. We can't reject. The results of our sample data are not significant. Have you ever heard people say statistical significance? That's what they're talking about. Alright. Well, I didn't want you to do that. So I said they were significant. That means that results support the alternative. If your data is significant, then your data supports the alternative hypothesis. If you fail to reject, your data is not significant. It does not support the alternative. Yeah. So I had wanted to look at a couple of problems from the 9194 homework. That is why I pushed that due date out. So I think this is problem number 1 in that 9194 homework. You are performing a right-tailed test with a test statistic z equals 2.06. Find the p-value. So I always have to draw a picture. That's the way my brain works. So if it's a right-tailed test, we are looking for the area under the normal curve to the right of a given value. And in this case, they're giving me a z. So I'm looking for the area under the curve to the right of a z value of 2.06. So I am looking for the probability that z is greater than 2.06 because it's a right-tailed test to the right of that z value. So that is a normal distribution with a lower limit of 2.06, an upper limit of infinity. Since we are talking about z values, this is a standard normal distribution. So the mean is 0 and the standard deviation is 1. So when we have z scores, that is standard normal. So mu is 0 and sigma is 1. Okay, so let's go over to our calculator, go to our distributions. We're doing a normal with a mean of, a lower limit of 2.06, an upper limit of infinity, mean of 0, standard deviation of 1. So the p-value is 0.019699. Zero, 1. Seven. So do I reject or fail to reject the null hypothesis? Well, it depends. It depends on what my preconceived alpha is. If I choose an alpha of 0.05, which is fairly typical, this p-value is lower than 0.05. 0.02 is smaller than 0.05. So if alpha were 0.05, we would reject the null hypothesis, whatever it is. Okay, the next problem deals with a t-test. And since we're using a t-test, it's still right-tailed, left-tailed, just like before. But instead of using the normal distribution, we would use the t-distribution. You are performing a left-tailed t-test with a sample size of 25. If alpha is 0.005 and your test statistic t is negative 1.9, do we reject or fail to reject? I have to draw a picture. So we're performing a left tail test. And since t is negative, it is over to the left of the mean in the student's t, which is 0. So it is over there to the left of there. Okay, so I need to find the p-value, which is the area under the curve to the left of a t-score of negative 1.9. So the p-value is this area under the curve. And the p-value is the probability that we get a t less than 1.9, whatever that is. And that is going to be a TCDF. And what do we have to put in our t distribution? The only thing we have to put in there is the lower limit and the degrees of freedom. So let me go over here. I don't have everything written down. So the TCDF is number 6. The lower limit is negative 1 times 10 to the 99. Let me write this here, which is a little bit neater. The upper is the negative 1.9. Our degrees of freedom, we had a sample size of 25, so that's going to be 24. For some reason, when I wrote this on my note paper, I didn't write the upper limit. All right, so what's our upper limit? Negative 1.9, and our degrees of freedom, 24. Degrees of freedom is our sample size minus 1. I get 0.03. I only need a couple of I probably need 3 decimal places because I'm comparing it to 0.005. So what do we get for our p-value? Our p-value is approximately 0.035. 0.035. Okay, so compare that to 0.005. Well, 0.03 is bigger than 0.005. That is a bigger number. 0.03 is larger than our preconceived preset alpha. So if the p is high, the null must fly. So if my p-value is larger than my alpha, I cannot reject the null hypothesis. So I fail to reject. Now, my gut feeling is 99% of you just guessed until you got it right. You only have 2 choices. Either guess reject or fail to reject. One's right and one's incorrect. So that would be my guess what you did. That's the reason it's failed to reject. Because the p-value is greater than alpha. Not that I've been around a long time, I've been around. And I try, when I design the course in my open math, not to give any true false or that one or that one. I try not to give this kind of question because you guess till you get it right. You get what, 3 guesses? So if you guess it wrong the first time, you guess the other guess and get it right. I've had people walk into my office. I said, how'd you get all those correct? I just guessed. So I got it right. All right, let's do some hypothesis testing. In a hypothesis test problem, you may see the words such as the level of significance is 1%. That 1% is your preconceived preset alpha. So that is the level of significance you choose. And it depends on how serious a type 1 error is to you. If a type 1 error is serious, then you're going to want alpha to be as small as possible. The statistician setting up the hypothesis test selects the value of alpha to use before collecting the sample data. If no level of significance is given, a common standard to use is alpha's 0.05. When you calculate the p-value and draw the picture, the p-value is the area in the left tail, the right tail, or split evenly in the left and the right tail. For this reason, we call the hypothesis test either left, right, or two-tailed. The alternative hypothesis, H sub A, or in your problems in this section, it may be H sub 1, tells you if the test is left, right, or two-tailed. It is the key to conducting the appropriate test. And you must know this. You must know if it's left, right, or two-tailed. Either to find the p-value using the normal distribution, you have to know what tail you're using. Or in a minute, we're going to get a lovely thing called a t-test and a z-test. But you have to tell your calculator if it's left-tailed, right-tailed, or two-tailed. That's one thing you have to tell your calculator. Thinking about the meaning of the p-value, a data analyst and anyone else should have more confidence that he or she made the correct decision to reject the null hypothesis with a smaller p-value. For example, 0.001 as opposed to 0.04. Both of those are less than 0.05, which is the typical alpha that we use. But we should be more confident that we're in the rejection of the null hypothesis, the smaller that our p-value is. The bread example, the p-value was 0. We had no qualms whatsoever saying that the mean height of loaves of bread is greater than 15. Our sample data was significant. It supported the conclusion that the mean height was greater than 15 centimeters. Similarly, for a large p-value, such as 0.4, as opposed to a p-value of 0.056, both are greater than 0.05. A data analyst should have more confidence that she or he made the correct decision and not rejecting the null hypothesis. This makes the data analyst use judgment rather than mindlessly applying rules. The following examples illustrate a left, right, and a two-tailed test. If the alternative hypothesis contains less than, that is a left-tailed test. So the p-value is the area to the left of whatever you get from your sample data, for the mean for your sample data. So this number right here, this value here is based on our data. So it would be the mean of your sample data. Now, even though our alternative is less than, this particular problem states the null as equals. It really doesn't matter if we use equals or greater than or equal to. They're the same thing in this case. The reason being is that when we conduct the hypothesis test and we find the p-value, it is based on the alternative being less than. So we're looking for a p-value, a probability of a value less than whatever we get from our data. So the alternative tells us this is a left-tailed test. So it really doesn't matter if the null is equal or greater than or equal to. Both of those would be correct. All right. Our right-tailed test. Now, in this particular example, we're using a proportion, which is okay. We are going to do examples of conducting a hypothesis test on a proportion. Remember, a proportion is when we're looking at a percentage of our population, we would be using a proportion test. So our proportion in our alternative hypothesis is that p is greater than 0.2. Since we're using greater than in our alternative hypothesis, greater than is to the right. So that is a right-tailed test. So the alternative hypothesis tells you if it's left-tailed, less than, or right-tailed, greater than. And again, the null hypothesis, because it's contradictory to the alternative, if the alternative is greater than, the null would be less than or equal to, or equals. They mean the same thing because what you're testing against is a p-value found from your alternative hypothesis. You're looking at a right-tailed test, so you're looking for a p-value, a probability of getting a value greater than whatever you get from your sample data. So again, this value right here, comes from your sample data. Okay, a two-tailed test. If your alternative hypothesis contains not equal to, then your alternative hypothesis would be equal to. That's a two-tailed test. In this case, we're using proportions. So if we're looking at a proportion, we're looking at a binomial distribution. So we're going to be using the normal approximation to the binomial. That's what we're going to be using. And so when I go to my calculator, and I use the normal approximation to the binomial, chances are I would find this over here. Because I know what that value is from my sample data. And I would probably, using that normal distribution, find the probability to the left. That would be the easiest thing to do. That's half my p-value. So for example, I conducted this test, I don't know, and I get that this value is 0.2. So the area to the left, or whatever that value is 0.2. Then the p-value is twice that. We'll do a problem like this in just a second. But based on my sample data, I'm either going to get the value on the right or the value on the left. And the easiest probability to find using the normal CDF is the area to the left. So this area over here to the left would be the easiest to find. And the p-value is just twice whatever that is. So if it's a two-tailed test, if you find the area in one tail or the other, you have to multiply it by 2 to get the p-value. And I think you have a problem like that in one of the sections where you have to double the p-value. All right, let's do a problem. Jeffrey, as an 8-year-old, established a mean time of 16.43 seconds for swimming the 25-yard freestyle. with a standard deviation of 0.8 seconds. His dad, Frank, thought that Jeffrey could swim the 25-yard freestyle faster using goggles. Frank bought Jeffrey a new pair of expensive goggles and timed Jeffrey for 15 25-yard freestyle swims. For the 15 swims, Jeffrey's mean time was 16 seconds. Frank thought that the goggles helped Jeffrey to swim faster than his previous average of 16.43. Conduct a hypothesis test using a preset alpha equals 0.05. Assume that the swim times for the 25-yard freestyle are normal. So the first thing we want to do is create the two hypotheses, the null and the alternative. So reading the problem, what is Frank trying to prove? That the mean swim time is less than it was before. That the goggles make a difference. So what is he trying to prove? He's trying to prove that the mean is less than a previous mean. That's the alternative. So the alternative hypothesis is that the mean swim time, now that he has these new expensive goggles, is less than what it was before. So this is the alternative. So what's the null? Well, you could write it one of two ways. Now, what I would do, because I'm old school, and that's the way that I've been doing it since the 70s when I first took statistics a million years ago. Or you could write it as equals. Because you're testing this, the alternative, it really doesn't matter if you write it less than or equal to, or excuse me, greater than or equal to or equals. It really doesn't matter. Okay, so let's think about this. Since I'm testing and my alternative hypothesis less than, this is a left-tailed test. Less than, left-tailed. So this is going to look like this. Since that is less than, this is left-tailed. So if I draw a picture, which I have to do, what is the probability that purely by random chance, this young man, Jeffrey, swam faster than 16 seconds for the 25-yard freestyle? So the p-value is right here. So it is the probability that I get a value of 16 or smaller. So the p-value is equal to -1 times 10 to the 99. Oops. Sorry about that, folks. Let me erase. I need to put a normal distribution in there. So it is going to be a normal distribution with a lower limit of negative infinity, an upper limit of 16 with a mean of 16.43. And the standard deviation that we are going to use is the standard error. And the standard error is sigma over the square root of n. And what did he calculate sigma? To be 0.8. And how many swims did this young man do? Did he do 15? So we're going to use 0.8 over the square root of 15. Okay, so that is going to give me the p-value. So I'm going to go to my distributions. We're going to do a normal CDF, number 2. Lower limit is negative infinity, upper limit is 16. The mean is 16.43. And the standard deviation is 0.8 divided by the square root of 15. That look good? 0.02. So the p-value is approximately 0.02. So now we're going to compare the p-value that we calculated with our preconceived preset alpha. And what did we set our alpha to be? 0.05, which is typical. If it's not stated in the problem, then that's what we're going to use. The p-value, 0.02, is less than 0.05. If the p is low, then null. Let's go. So we're going to reject the null hypothesis. What's that mean? Your data is significant. Your sample data supports the conclusion that the swimming goggles made a difference, that he's actually swimming faster on average than he did before. We are supporting the alternative hypothesis that the mean time to swim the 25-yard freestyle is less than 16. All right, so we make a decision. Since the p-value is less than alpha, we are going to reject the null hypothesis. That means we reject mu is equal to 16.43. In other words, you do not think Jeffrey swims the 25-yard freestyle in 16.43 seconds, but faster with the new goggles. So how do we state our conclusion? At a 5% significance level, again, that is your chosen alpha. Alpha's 0.05, which equates to 5%. At a 5% significance level, we conclude that Jeffrey swims faster using the new goggles. The sample data show there is sufficient evidence that Jeffrey's mean time to swim the 25-yard freestyle is less than 16.43 seconds. When you reject the null hypothesis, you will see always in our conclusion that we say our sample data shows there's sufficient evidence. So when you reject, the sample data is significant and it's sufficient for us to do that. If you fail to reject, then the data that you've collected is not sufficient. Okay, do you want to know the easy way to do this? I'm going to show you the hard way so you can show you the easy way. We're going to use a z-test. And the z-test is found in your stats menu over in your test menu. And number one is a z-test. You use a z-test when your distribution is normal and you know the standard deviation of the population. If you don't, then you're going to use a t-test. So for this particular example, Dad had been clocking this young man for so long, he knew the standard deviation. So we can use that as a population standard deviation. So we're going to do number one. And we're going to use stats because I don't actually have Frank's raw data available to me. But I do know the mean and I do know the standard deviation. So we're going to use stats. Okay, so the mean is the mean from the null hypothesis. The null hypothesis was that the average was greater than or equal to 16.43. So that's what we're going to use. The standard deviation that Frank had calculated over the years is 0.8. The X bar is the average that Frank calculated with the samples, the 15 swims with the new goggles. So that was 16, correct? And he did that, there was 15 swims, correct? He clocked him for 15 swims and that's how he found the average. So N is 15. So what do I need to know? I need to know next, is it two-tailed? That's the not equal to. Left-tailed, which is less than, or right-tailed, which is greater than. And that is based on my alternative hypothesis. What was your alternative hypothesis? That mu was less than 16? So you're going to pick less than. Highlight that by hitting enter. And I think we're good to go. The average that this young man had swam before was 16.43. Is that correct? Yeah. The standard deviation is 0.8. The new average that he got after getting the new goggles was 16. He did that for 15 races, and we're doing a left-tailed. So I'm going to go down to calculate and highlight it and hit enter. What's the p-value? That's this right here. P is point, is that what we got? Now you have to make the decision. I mean, it calculated the p-value for you. Woo-hoo. Lucky me. But now you still have to make the decision. Since that p-value is less than 0.05, again, P is low, the nulls must go. So I'm going to reject the null hypothesis. All it does is save all that calculation of the p-value for me. And where this is really nice is when you have two-tailed, and you have to remember that you're multiplying. If you don't use a z-test or a t-test with a two-tailed test, you have to remember to multiply the p-value by 2. All right, let's try another one. Now, I'm going to let you put this data in your calculator. I already have it in there. So I'm going to give you 2 minutes to do it. Just so we can practice, use our calculator for actual data and just not the stats that are given to it. A football coach records the mean weight that his players can bench press as 275 pounds. With a standard deviation of 55 pounds. 3 of his players thought that the mean weight was more than that amount. They asked 30 of their teammates for their estimated maximum lift on the bench press exercise. The data ranged from 205 pounds to 385 pounds. And the actual weights are listed. I'm going to give you a table here in a second that you're going to put in your calculator. Conduct a hypothesis test using a 2.5% level of significance, or alpha is 0.025, to determine if the bench press mean is more than 275. So just by the stating of more than, this is going to be right-tailed, correct? You're going to be testing if the mean is greater than 275. All right. So here's your data. So put the weight in one list and put the frequency in another list. So maybe put the weight in L1 and the frequency in L2. Give you a second to do that. Are we good? Okay. So let's go back to the problem. These are null and alternative hypotheses. We're conducting a hypothesis test using a 2.5% level of significance. So alpha is 2.5% or 0.025. And we're trying to determine if the mean based on this sample data is actually greater than what the coach says it is, which is 275. So if what we're trying to prove based on this sample data is that the mean is higher than what the coach claims, that's the alternative, isn't it? So the alternative hypothesis is that the mean weight is higher than what the coach thinks it is. So what's the null hypothesis? Well, it's either less than or equal to, or you could use equal. It does not matter. Okay, so since this is greater than, this is a right-tailed test. And I can calculate that X bar. I can calculate that from my data. And I can use the normal distribution to find the p-value, or I can just put this in my calculator. I'm going to first, real quick, go ahead and calculate the X bar just so we can see how that's calculated if we don't recall how to do that. So we go to our stat menu, we go to calculate, and we're going to calculate the one variable statistics based on the data that we put in our calculator. So one variable statistics, my list I put in L1, and my frequency I put in L2. So I need to tell my calculator that the frequency is in L2. That's the number of times we got that weight bench pressed. So then we're going to calculate. So I get 286. So the average based on this sample data was 286.2. So what's the probability that I get a value of 286.2 or more extreme based on that data if the average is actually 275? So I could use the normal distribution to find the p-value. The p-value is the normal distribution, the area under the curve, from 286.2 to infinity, with an average of 275 and a standard deviation. What do we have? 55 over, what was my sample size, 30? So I could do it that way and calculate the p-value. I could do that. Or I can just use the z-test. I'm going to do that because I'm lazy. Not that I think you're lazy, but I think you're lazy. So I'm going to go to stat, and I'm going over to test. And I'm going to do a z-test on that data. So instead of using stats, I have to go over to data. And I have to tell my calculator where my data is. Okay, well, what's my mean? The coach says it's 275. So we're going to put that in. My standard deviation was what, 55? And my data is in L1 and my frequency is L2. So I do need to tell my calculator that I do have a frequency and it's in L2. All right, this is a right-tailed test, correct? Because we're looking at mu is greater than 275. So I need to change this to a right-tailed test, greater than. Okay. I haven't got it. Lisa, do that again. Okay, is that good? Coach says it's 275 with a standard deviation of 55. I have my data that I collected in L1 with a frequency of each data value occurring in L2. I'm looking at a right-tailed test, so greater than, and now we're going to calculate. You can draw this, which is kind of cool. It'll draw the normal distribution and show you the area to the right. We'll do that next. Calculate. Okay, what's the p-value? The p is high. 0.13 is high. Way bigger than the alpha of 0.04. P is high, the null must fly. The sample data do not support the claim that the mean weight these players are bench pressing is greater than 275. So our p-value was 0.13. The p-value is greater than our established alpha. So alpha was 0.025. Is that what we were using? So the p-value is greater than alpha. If the p is high, the null must fly. So we fail to reject the null hypothesis. The sample data does not support the claim that the mean weight bench press by these players is greater than 275 pounds. So our sample data does not support that conclusion. So our decision, since alpha is less than P, we do not reject the null hypothesis. At a 2.5% level of significance from the sample data, there is not sufficient evidence to conclude that the true mean weight lifted is more than 275 pounds. So it appears coach was right. Always trust your coach. So many of you have coaches in whatever sport, either ag or basketball or whatever sport you're playing, baseball. All right. I don't think we have time for this. I think we'll quit. And we'll pick this up on Wednesday and finish up our examples. Are there any questions? Okay, so we've sufficiently covered enough for you to do the first set of homework 9.1 to 9.4. We will finish up this examples for you to do the problems in 9.5 and 9.6 on Wednesday. Okay.